Good morning, everyone. This next video, again, is going to be just an overview of some of the topics in our Further Math Calculus option from sections G, H, and I, just to kind of focus you in on a few things that you may want to work on. I will post a worksheet, as usual, after each one of these short little videos. First one, we dealt with limits, continuity, and, of course, some differentiation. And as I mentioned, that's kind of the building blocks of what you would eventually call an analysis course. For some of you, you'll experience that. Here, we're moving on, of course, to integration. So it's kind of all jumbled together, but of course, a big part of integration starts with Riemann sums, and understanding that we can have this thing called an upper sum, a lower sum, left endpoint, right endpoint, midpoint. We don't have to have uniform kind of bases for these rectangles that are put underneath a curve to get an area, but it's nice. Using Riemann sums, we can even create a limit and use some summation notation and summation properties to get an exact area under the curve from more of a numeric start, but making use of limits as that n goes to infinity to get the exact value. So there are some things about Riemann sums that should bring back some memories from a BC Calc course. Of course, you can't say much about Riemann sums and area under a curve without really dealing with average value of a function. So you'll see that. Not much else to say about that one. The fundamental theorem of calculus and the second fundamental theorem, of course, that was a way to evaluate definite integrals. And sometimes if a function is given as an integral, we can differentiate it. And that's where the second fundamental theorem comes into play. So the topics that you're going to see here aren't really any different than what you've seen in the past. Some of the notation may be a little bit different. We also deal with some improper integrals. Now, improper integrals can be improper for a variety of reasons. The one we tend to focus on here is when one of the limits of integration is infinity, or maybe somewhere in between the limits we have an undefined term or where it's not continuous. When working with improper integrals, of course, we always want to be able to split things up in such a way that we may have to use L'Hopital's rule, because to evaluate an improper integral, we're really creating the integral and making a limit. So just be aware of that. We do use these words like convergent and divergent. Simple comparison is what we're going to use. This does not mean Taylor series, Maclaurin series. We'll get to that actually in one of our next short videos. So it's all centered around kind of area under a curve, definite integral, and proper Riemann sums. Now, there are a few things that are just a little bit different than what we maybe have seen in the past. And that's one thing I want to point out. One could be as simple as this. Let's say we want to write a series approximation for this integral. Now, we know that to evaluate that integral, we would look for some type of a procedural formula, but there's not one that we know of. So there are other methods. But for now, if we want an approximation, we could, of course, think of upper sum and lower sum if this happened to be a finite number. But without that, we've got a little problem. So all we want to do is write it as a series. So it really comes down to making it a series. And we could write it as a series as I, we'll use that as our index, from 0 to infinity, of 1 over radical I plus 1. And if we add all of these together, okay, we should have a series that approximates the value. Because again, we're talking about the base of these to be basically infinitely small. So it seems like a complicated problem, but it's not. One other thing that I think is important. If we have a function from a constant to infinity. And it happens to be decreasing. Then what we can do is we can talk about lower sums and upper sums. For example, I can say the lower sum is going to be the summation as I goes from a to infinity, the f of I plus 1, and then the upper sum on the other end could be considered the sum as I goes from a to infinity of simply the f of I. Because again, if we have a decreasing function, wherever a is, I'm going all the way to infinity. Here, to get the lower sum, I'm always going to be using that that right endpoint. Okay, so there's the plus 1. For the upper sum, I'm going to be using this one. And then what we have as an inequality is just the actual integral in between. So the value of this integral can be split between the upper sum and lower sum, and we already knew that. The only difference here is we're using summation statements to work with it. So what eventually can happen is this, is if I can evaluate this limit through methods and evaluate this summation, then I can know the exact value of the integral, the indefinite integral. So there's a lot more of that type of notation and requirement that you'll see in the examples. Now, of course, if it's increasing, be kind of the same idea, except the lower is going to just be with the I, and the upper will be with the I plus 1. So I don't want to take the time to even write that out. So as I said, this is intended just to be a kind of a focus type video. Many of the problems you'll see will involve just the fundamental theorem and the second fundamental theorem, so they're very numeric. There will be a variety of improper integrals, Riemann sums, but when we deal with Riemann sums, it's very common that we want to write some of these inequalities, or if we're given an inequality, we interpret what that's really meaning, whether we're dealing with a decreasing or increasing function based on some of these summation statements. So, very shortly, I will post the short worksheet, and hopefully you're making progress. Continue to read the sections, and if you have any questions, please let me know, and enjoy this for the weekend.